Dear student, today we start with the model location and more in step index fiber. It is the preceding lecture from the previous onward. After solving the wave equation for step index fiber, now we'll move toward in order to solving it for model locations. For that, first of all, the solution of this beta component that can be determined from the boundary condition. So, in order to find boundary condition, there is a requirement of this tangential component of this E pi as well as Ez. That is E inside and outside the dielectric at interface when r radius is equal to a, and that must be same for when we are apply for h phi hz. So we assume that ez1 is equal to ez2 and e phi 1 is equal to e phi 2 about the electric component, and about the magnetic component we take hz1 is equal to hz2 inside and outside the dielectric media, inside the optical fiber outside, and similar h5 and h5 2. Now this question, or we can write in another term, ez1 minus ez2 is equal to 0. Now this question can be written by taking the Basel function for first kind of order V, as well as the modified Basel function of second kind, that is K P W R. So if we take this minus this is equal to 0, in this expression of this these Basel function, the value of u, that is represented u square is equal to omega square mu epsilon 1 minus beta square, which we can write this combinedly as a propagation part of the one side of the boundary, which is equal to a b1 square minus b square, and on the another side, that is outside the boundary, that we can consider omega, this w square is equal to beta square minus omega square mu epsilon 2. So this is equal to basically a b square minus beta 2 square. So this condition we can find for tangential component, another z1 is minus hz2 is equal to beta, this Basel function of first kind JV UA minus d kv, that is the Basel modified Basel function of second kind with W is also equal to 0. Now using these Ez and Hz component, we can also find the value for E phi and H phi, which we can written for this E phi 1 minus E phi 2. Like we have used this previous equation of E phi, which we use in order to solve for the wave propagation equation for the step index fiber, which is equal to a minus j q square bracket start beta r dez upon d phi plus mu epsilon omega dhz upon dr bracket close. Now this e phi, for this phi 1 we may write minus j, instead of q we put the value of this u from the previous part, and a, a is the same equation which we have write beta r, instead of r we write a, r is equal to a, and Ez is equal to, we have put the value of a j v u a. Now the value of a j v u a is available, but e raised power j v phi, when we are differential with respect to d upon d phi, we got the value of j v. Now minus, now we have to put a mu omega dhz upon dr. So for that we have taken bjvua. Now when we apply it here, mu omega is there, b is also there, this JV is also become the derivative part of that. And whenever we take its derivative, because there is a no such constant component of dr is to be there in omega t, that's why we have to written in j dash vua. Now similar when we have applied for this minus e2, in which the component of c is to be came here for second component, and here instead of q we put omega square, rest part is same minus this part is to be there, and again this derivative of kv, because dr part is not to be there, that's why kv dash is to be came here. Now second expression, we have also take the wave propagation equation for the H5 component, the field component which is around the fiber. So that is equal to minus j q square beta upon r dhz upon d phi plus epsilon omega dez upon dr. Now for this, first of all we put the component of dhz at here. So whenever we apply this component, minus j instead of q we put u, and beta upon a, then b is same part is to become jv is also to become here, but for whenever ejv is e to the power jv is when differentiate, the JV component is to be dependent upon that, so that is not showing the any differentiation of this, and e to the power JV that is become JV, and another component is to be cancelled out. Now next component which we have used, that component is basically the second component of EZ, which is available from the previous part, and the component is j dash v is to be taken because there is a no dependent of this dr component is to be there in this Bessel function of first kind. Then we have taken minus h phi 2, for that this minus this part is to be taken. Whenever we put that here, the same constraint we have to be used at here, plus this component is came from the previous question. Similar, we got these two expressions, e phi 1 minus e phi 2, with the same solution. Now next we can put equation from previous 5 to 8 set of 4 equations with the 4 unknowns a b c d z are present. So from the first, if we say there is a jvu 0 for B minus kVA that is obtained, and corresponding value of that we have obtained in the expression for Ez E phi minus E phi 2, and each component is to be put at here with this J dash V UA at here, and similar this is the part next, and for hz h5 minus h2, this part is 0 jvu, this part is 0, d is to be there. So that is means c and d is here in the case of h5 minus h5, and in e5 1 e5 minus e5 2 we have a component of a and c are to be there, and corresponding their value of a b c d from the e5 1 minus e5 2 and h5 1 minus h5 2, and this is equal to 0. Solution of this equation is exist if a determinant of this coefficient is equal to be 0. So evaluation of this determinant yield with the following eigen equation for this beta, and if we solve it, and we got a component of this j dash v ua upon u j v ua plus k dash v w upon w k v w a, and next component is basically a beta 1 square j v ua u j v ua plus beta 2 square k dash v w a WKV WA, which is equal to a beta V upon a 1 upon U square plus 1 upon W square square. This equation is basically known as the general characteristics equation of any kind of mood. We can derive any kind of mood from here. In order to deliberate any kind of mood, uh, we have the representation of like that. We can easily represent the modes in the step index fiber. There are basically three kind of mode in the step index fiber: TE, TM, and there is a HE or EH. First is transverse electronic mode in which TeVm is to be there, and then there is a transverse magnetic field mode TMVm there. Hybrid mode HEVM and EHVM is to be there. Now, if we take Hz is equal to 0, all the field component are expressed in term of this Ez and no magnetic component in this direction, then we can call it as a TM mode. TE mode is that in which Ez component is 0 is known as the T. Hybrid mode is that when no component of Ez or Hz is equal to 0. None of these are 0. If Hz is dominant, then we represent EH mode. If Ez is dominant, then we represent HE mode. So this kind of representation we can write while representing the mode, because previous question we can find the different kind of mode easily. These three mode further characterized into two indices. One is we write TEVM. V shows the number of half cycle variation in the azimuth plane. There is a V is equal to whether 0, V is equal to 1, like for 0 this is 0, for 1 this is the representation, for V2 then this is the representation. M is shows the field variation in the radial direction, or 0 crossing in radiation direction to the fiber. Mean to say that from starting center to outer word, the variation I am that represent. If V is 0, the function e j power V remain constant for all value of phi, and result symmetrical circular mode is to be there. If V is equal to 1, that is for only circular mode. If V is equal to 1, we get a one cyclic variation, like one cyclic variations. V2, we get another one cyclic variation is to be there. Similarly, we represent like there is a circular symmetry for the field when V0, M0, and a circular variation that is shown here. Now, when this V is equal to 1 and M is equal to 1, in that case, this is 0, but the component of maximum that is lies in two part. Now, here the value of M that is remain the same. There is a variation of circle, but the value of V is that is changes to two part. Now next there is a V is equal to 2. Further there is a crossing the mode, and that is correct. There is a maximum height here, maximum height here, maximum height here, maximum height here. But M is equal to 1. Now, if we have to represent in term of this V is equal to 0, and this is the phi angle. The mode is basically conserved in the core of the fiber for that fiber axis, and field variation is this part is of the field is also present in the cladding, but maximum desire is that part should be constrained in the field. That's why this V0 mode in which TE01, TM01, they are concentratedly focusing at the center of this, mainly which is the condition of propagation is required. As we go readily, these are going depleted. So another M show a radial field distribution of R is equal to, which is the function of radial, which is a Bessel function. It shows zero crossing in the radial direction uh, with the m minus 1 crossing in the radial direction. Like that when there is a v0 that is represent the circularity with m1. M1 means that is also equal to 0, radial direction of this in order to a representation of m. Now when there is a m is equal to 2, the outside mode that is represent there is a 2 another outside mode, 2 minus 1 1 another outside is to be present. When m is equal to 3, after outside that represent there is a remaining 1, after putting 2 there is a remaining 1. So similar with the variation of m 1 2 3, the field variation is easily shown in this expression. There is a circular, two circle with outside ring, one circle with the two rings. They are now for from these expression which we have written for modulation for v is equal to 0. Now the value of v is equal to that is goes to 0. You see 0. This is also 0. And for that j naught dash is equal to basically a minus j ua, and k naught dash that ua is equal to basically a minus k1 ua. So either equation in the first bracket is 0, of the second equation is 0. So first part of this expression, instead of this we may write j1 uj naught that is, and instead of k naught we put k1 ua that is equal to a 0. This is basically represent the characteristic equation for e0 m mode. Similar, if we take the second part in the second bracket, this beta 1 square is equal beta 1 square j1 j naught dash ua is equal to, we have put j1 ua divide by this u j naught ua we have put directly, instead of this derivative function k naught dash wa we put k1 wa. So this is represent the tm0m mode. So mathematical representation is easily we can put here. Now from this question, multiple solution due to oscillation variation of this j naught x and j1x as multiple 0 are crossing. So depending upon the radius of the core, like here radius is a, there may be have a m multiple solution. Like there is a TE01 signify the circular symmetry for first solution, TE0 that is circular symmetry for the second, and for mth solution there will be a m minus 1 number of 0 in the field, and can be shown in the representation no intensity representing the zero crossing. So we can easily estimate mod formation like for this when v is equal to 0 m is equal to 1, this is a circle part is to be there. For v is equal to 0 and m is equal to 2, this is for first v is equal to 0 represent the circular symmetry, and when m 2 is equal to, this means there is a outside one mode is to be there in the this part. Now when m is equal to 3, in this aside from this center one there is a this this part highest m3, and this part is to be there. So v is not 0. The general characteristics uh, equation representing the hybrid mode in the fiber. For a hybrid mode, v is equal greater than 0 and 1 or more 0, they are basically crossing the azimuth directions. So that's why there is a circular two ring, three ring that to be there. Now for both we have a median ray as well as the skew ray. Uh, from this V and M. In order to representation the intensity at the fiber, we can easily represent as we have put V is equal to 0 in the median ray, and we have evaluated for mode 1, 2, 3 crossing for M, that is for single, double and triple ring. Now another, when in the skew ray, when V is basically varying here, M is equal to just a 1, that is a single passing. In that case, when there is a V is equal to 1 1, in that case it is splitted into two part, maxima at here, maxima at here. When there is a two, there is a two maxima at here, two maxima is at here. And when there is a three maxima in one side, three maxima is on the another side. That is when there is a four maxima basically on the one side, one, two, three, four, and four is in the other side. When there is a V is equal to five maxima in this side and five maxima on that side for this mode one representation for a skew ray. So median ray and skew ray is easily we can represent. Now cross-sectional view of transverse electric wave for whole lowest mode in the step index fiber. First of all, we consider that the E01 mode. Here, the 01 mode means there is a circular representation of the electric field, and it is rotating in the field is moving in the clockwise direction. And from the center magnetic field, they are naturally perpendicular to this E. If E is in this way, M is in outer way, representing the same way in order to represent. Now for the hybrid mode, when there is a this V is equal to 1 and M is equal to 1. So for that HE is to be formed, V is equal to 1, and there is a field line which are to be represent half field line at here, half field line at here. And for H21 there is a four maxima is to be there, one maxima at here, one maxima at here, one maxima at here, one. So this is H21 representation. So for lowest mode in the step index fiber we can represent very easily. Hybrid mode HE11 and H21, the maxima which is very clear from this pointer we have already represented. Now next is this is all about the mode representation. Next, V number of the optical fiber. Numerical aperture of the fiber gives the information about the refractive index difference only. Numerical aperture does not consider the radius of the pole, which do not truly characterize the fiber. So we introduce V number parameter to characterize the fiber. We know that U square is equal to omega square mu epsilon 1 for the inside the boundary, and W square is equal to minus W square omega square mu epsilon 2 outside the boundary. If we add both together, W square plus U square, we got this minus omega square mu epsilon 2 plus omega square mu epsilon 1. Here the common factor is the omega and mu. Or take these, and another factor is that from this omega mu we got this beta 1 square minus beta 2 square, and whenever these are the basically related to the propagation part, and both are related to the beta naught value, beta naught. So beta naught for the boundary condition interface, like n1 for the n1 square minus beta naught square, n2 for the outside, that is for core and for cladding. Beta naught square is the common part. Now from this expression, if we multiply both sides by a, like a square, a is basically the radius of the core, and this a square is to be multiplied, we got v square is equal to a square u square plus w square. And when we apply at here, beta naught square is equal to basically the component of 2 pi upon lambda propagation part into a square into n1 square minus n2 square. Now instead of this v square we consider only the v, then a is the component 2 pi upon lambda, and this is came under the under root, and this part is basically equal to the numerical aperture, and another factor c is equal to f lambda. Now lambda is equal to c upon f. F is goes to up, and 2 pi f is equal to become omega. A omega upon c numerical aperture. V is the number more comprehensive characteristics parameter. It includes numerical aperture, radius, frequency component of the optical link. V number depend upon on the this omega, and other component are constant for the particular. So it is also represent as a normalized frequency. We can also represent in term of a normal frequency. Another is the normalized phase constant. For wave propagation, this beta boundary condition for propagation followed condition beta that should be lie between this beta 2 and beta 1. That is related to beta n2 for this core and beta naught n1 for the sorry, this is for clad and this is for the cloud, and beta is lie between this for the propagation part. So if we have to divide by beta naught, the component phase constants for vacuum we obtain n square, n2 divided by beta naught less than n1. This is basically the n effective. N effective is the effective refractive index experienced by this wave in the fiber. As propagation is not only in the core, it is also in the clad part. So propagation phase propagation constant for the wave in core and cladding is entirely different due to their different movement. Practically, wave cannot travel at two different constants. So wave are short of try to travel at core and cladding interface. So there is a kind of mutual dt in term of this beta. It should be between this beta 1 and this beta 2. So physical significance of this previous question that if beta is near to beta 2, most of the part is propagate in the cladding. Wave is not propagating in the cladding, it is represent actually the leaky wave which is leak from the propagation part. If B is near to the so beta is near to the beta 1, most of the part is confined to the core and wave is propagate in the guide mode, which is desirable for data security and good communication. So beta should be greater than omega square mu epsilon 2 and near to the beta 1. That is the requirement. The effective index should be near to the n1 and much larger than the n2, which is the desired. Now, similar to V number, we may define normalized phase constants beta in term of place of B in term of beta. B is basically based on that n effective square minus n2 square divided by n1 square minus n2 square. So if we are not taking the square, we may represent approximately equal to n effective minus n2 divided by n1 minus n2. Okay, so number 16 is to be came out for n effective that is equal to the n2. Then that's mean beta, that is when both are equal. This mean beta is this part is become 0. Mean totally propagate in the cladding part. Cladding part is not the basically propagating part. So generally we define it as a leaky mode. The wave is basically no information is received at the receiving end, and we forming a leaky mode at here. now for n effective is equal to n1. In that case this n1 minus n2, n1 and minus n2, and we got a beta is equal to 1. Both are cancelled out. Basically, we have confined within the core, that is the guided mode. So B is basically the normalized phase constant that is lie between this 0 value as well as between this 1 in order to propagate, not reaches at here in order to forming a leaky mode, and that is the desired ideal mode which is required. So we have another graph between the normalized propagation constant beta, sorry B, and a normalized frequency V parameter. B versus V number plot is more comprehensive than beta versus omega. Plot shows the variation of V with respect to V for different mode. HE11 mode propagate through the fiber even at very low V number dominant mode, and TE01 mode does not propagate till V number to be exceed 2.4. 2.405 is the exact if we put the standardized component of V in 2 pi a upon lambda n1 square minus n2 square, that is equal to or less than 2.405. If V number is less than equal to this is known as a single mode fiber, for a single mode fiber proper. And if it is wave is number is greater than 2.4, fiber is basically we have a multi-mode fiber and we can estimate the mode accordingly. So some of the problem which related to this V number I have described in this lecture is step index fiber has a core diameter of 50. A is basically we have radius is equal to divide 50 divided by 2, 25 micrometer. The fiber has numerical aperture Na 0.2. Estimate the total number of guided mode propagate in the fiber when it is operated at a wavelength of 1 micrometer. Normalized frequency formula V is equal to A 2 pi upon lambda into Na. A is equal to 25 into 10 to the power minus 6. Then 2 pi uh, 0.2 is there. Lambda is equal to 1 micrometer, 1 into 10 to the power minus 6. We got 31.4, around 32. The number of guided mode can be calculated. V square divided by 2 is the number of mode. When we calculate, we got 492.98. Hence, fiber is approximately 493 guided mode are to be there from this estimations. Another is step index fiber with core diameter of 80 micrometer and a relative index difference of 1.5% is operating at a wavelength of 0.85 micrometer. If core refractive index is 1.48, estimate the normalized frequency for fiber number of guided mode. The normalized frequency for a fiber V is equal to A 2 pi upon lambda or Na. Instead of Na, we write N1 under root 2 delta. So we have A is equal to 80 divided by 2, 40 into 10 to the power minus 6, 2 pi into N1 is equal to 1.48, 2 into delta is equal to 1.5 divided by 100 around 0.05 under the root 1 by 2, and lambda is equal to 0.85 into 10 to the power minus 6. So 75.8 mode 76 number are to be there. So number of guided mode that can be calculated V square divided by 2. Square of this one divided by 2 we got 2873 guided mode, and V number are 76 obtained from here. Now third example is step index fiber having a relative refractive index difference of 1.5% is operated at a wavelength of 0.85 micrometer. If core refractive index is 1.48, estimate the core diameter for single mode fiber. So we have the formula for V number for single mode fiber, that should be less than 2.405 or 2.4. So core radius formula V is equal to a 2 pi lambda or into Na. Na may be a n1 under root 2 delta. Now this is 2.4 is to be there. A we have to evaluate 2 pi n1 2 into this 0.015 divided by 0.85. We have to find the value of A. A is equal to 4 micrometer, which we calculated. Hence, the maximum core diameter for single mode fiber uh, operation of the fiber should be 8 micrometer that we can find. So by using this representation, similar we can utilize the B number for various evaluation. B is equal to also in the another N effective is representing that is also beta 1 divided by B naught square minus N square upon N1 square minus N2 square. This evaluation that can be there. Now if we want to say that we have a Na, instead of Na we may put uh, sine theta N1 square minus N2 square, and sometimes sine theta that is equal to a theta which is solid acceptance angle, and solid acceptance angle is equal to pi theta square. Then pi n1 square minus n2 square that we can put in the solid angle, like in the mode m we can calculate, like there is another formula. We can calculate m is equal to 2a. A is the area divided by lambda into that solid acceptance angle. A is equal to pi a square, and solid angle is equal to pi theta or pi n1 square minus n2 square that we can put, and m is equal to basically v square upon 2 that we can find. Uh, Part of this power flow and a polarization mode field diameter, which is also the extension version of this that we can do in next module. Thank you very much.